Let's do a few examples that make use of the multivariate chain rule. First up, let's look at a typical situation where we have multiple functions with multiple variables. But this time, let's evaluate the derivative at an actual point. We can use our usual techniques to do this, but because we're evaluating at a point, we can arrive at an answer without computing the derivative. Regardless, we do need to start with a dependency tree, which we write out as follows. Since we want dw dt, we'll trace the paths from w to t, so that the chain rule reads by adding these paths. Now this next part is where we will do things a bit differently than if we were computing a derivative function. We know the values of s and t, but it'll also help to know the values of x and y, which we can find by plugging in our values for s and t. The value of x is 1/4, while the value of y is 9. With that, we can now start computing derivatives. Starting with dw dx, the partial derivative is just y. And instead of writing y in terms of s and t, let's just figure out its value. We computed above that y equals 9, so dw dx is 9. dw dy is x plus 2y. And again, instead of writing this in terms of s and t, we know that x is 1/4 and y is 9. So we plug this in to get our value of dw dy. Finally, dx dt and dy dt are a bit more straightforward. We just compute them like we normally would and evaluate when s equals 1 and t equals 3. So now we're ready to put this all together to get the final answer. From our dependency tree, this is the derivative. And we've computed each of these values, so we plug them in to get this gross number out. And you'll notice that we never had to actually compute the derivative. We found the answer purely in terms of the component derivatives. So up until now, our composing functions have been relatively straightforward. Next up, let's take a curveball. Here are a bunch of functions. Let's find dw dt. Notice that every function has a t in it, and x also depends on y. This could make things interesting. But instead of panicking, we'll do what we normally do and create a dependency tree. W depends on x, y, and t. X on t and y, and y depends on s and t. We're after dw dt, so let's track all the paths. I'm also going to number them so we can track them when I write out the derivative. With the paths in place, we just need to write out the chain rule. Along path 1, we get this. Path 2 is a little bit longer. Now for path 3. And finally path 4. So our usual technique does work, even though it took a little bit longer. One last thing to note is that there are two dw dt's in the above equation, one on each side of the equal sign. Despite appearances, these are not the same thing. The one on the left is the total derivative, the derivative after we've traced every connection to t through both x and y. The one on the right is the derivative of w with respect to its t, the one that appears in the definition of w without worrying about either x or y. This is a failing of the notation, so just be wary that this could happen.